Okay, we have zoomed in on a stretch of data here. We go from 0.055 to 0.065. That's only a change of 0.01 newtons between these two lines. And we're only covering a couple of seconds here, so you can see the individual data points. What you notice is that it doesn't register the same thing all the time. It changes and goes up and down. And that is because the actual signal is deliberately dithered or jittered around so that you can get better resolution than the actual resolution of the device itself. The actual resolution, you notice that it only comes in at certain levels. It doesn't come anywhere, but it doesn't come in this level here. It's either here, or down a step, or up a step, etc. And that step corresponds to 1.7 millinewtons. That's 1.7 thousandths of a newton. The fact that you take a collection of points and can average over them means you can get an even more accurate result than that. So we'll turn on the statistics, and it will give you the what the mean is and the standard deviation. Now, in assessing what your error is, if we have let's say 10 seconds of data, 20 samples per second, that's 200 samples. So the standard deviation of the distribution is one thing, and at least theoretically, if it were a Gaussian distribution instead of a discrete distribution, you'd be entitled to take that standard deviation and divide it by the square root of 200, or 14, to get your actual standard error. Now, I don't believe it's going to be quite that good because it's not a Gaussian distribution, but your lab instructor will tell you what to do about the standard error. The one thing I will tell you is the accuracy of this experiment is extremely good compared to what you need to do the experiment.